Morning, everyone. This is SRSBS Maths and Science channel. So today we are going to be doing what they call paper 2 in physical sciences, which is chemistry, and the part of that we'll be busy with will be the chemical reactions. But before we go to those chemical reactions, we'll have to start from the basic concepts, and which is the understanding that one would have to have before one can go and attempt to master up the rates of chemical reactions. So to start off with, we'll look at the types of chemical reactions and try to look at the graphs that give us the better idea of how energy are involved in the chemical reactions. And from there, we'll then move over to what we call the Maxwell-Boltzmann's curve, which is also very important that we understand so that we can understand better why and how chemical reactions take place. But to start off with, we'll start by looking at the types of reactions that we've got in our chemistry. So mainly we divide our chemical reactions into two types that we call endothermic chemical reaction and exothermic chemical reaction, and this is how I define them. The types of chemical reaction that we've got, I said there are two types of those chemical reactions. First one is endothermic reaction. Second one is exothermic reaction. What is an endothermic reaction? An endothermic reaction is a reaction in which energy is absorbed from the surrounding. Just to give you an idea of how such reaction takes place, if you think about your refrigerator that you left at home, there is a gas that is found in the pipes that are coiled up in your refrigerator, and when you heat, that is, when you switch on the electricity, then the element in the refrigerator pipes heat up the gases. But those gases, because they want to take a lot of heat because of the reaction, they absorb a lot of heat, which results in the outer pipes becoming colder, whilst all the energy is absorbed by that gas, which is filled within those pipes that take all the energy from the surrounding, leaving the outer environment, in this case, the area around the pipes in your refrigerator, very cold. It's a good example of an endothermic reaction. This one takes heat away from the surrounding into itself. Then another example, if you take a salt called sodium nitrate and you dissolve it in water, you just measure the temperature of your water by your thermometer before the reaction starts. And then you add the salt, then you stir your solution with your thermometer in. You'll find that after you've just stirred some time, the temperature in your thermometer will be dropping, showing that the temperature of the surrounding, which is your container, is decreasing, shown by the thermometer. And that will also be a good example of an endothermic reaction. Now, we can move on and look at what we call the exothermic reaction, which is the second type of the chemical reaction. The exothermic reaction, it is the reaction in which energy is given out to the surrounding, and you are used to most of these types of chemical reactions. If you can think of yourself taking a match and then you're lighting up your candle, then the whole space becomes warmer. Why? Because as the chemical reaction is taking place, the organic substance in your candle burns in oxygen, releases that heat, and that heat is what is released out. So that reaction is an exothermic reaction. So what we just say that is just that in that type of reaction, energy is just given away, that is taken out to the surrounding. So in other words, the surrounding becomes warmer as the reaction takes place. Now we may continue now and look at the graphs, and let's try to interpret these graphs that we've got about these chemical reactions. Now in the first graph, I understand that if you may zoom the video, you'll just be able to see that clearly. In the first graph, you'll see then that this is in my axis, which is vertical. I've got the energy of the substances. Then on my horizontal axis, I've got the cause of the reaction. So when I've got a hypothetical chemical reaction, in other words, the reaction that is not from the elements or compounds that you know of, in this case, one of my reactants is R that reacts with another reactant, which is S, and this form my product, which is P. So when I go and put those substances on my energy curve, you will see then that before the reaction starts off, I've got the energy for the substances R and S, which is at that amount. If you look at the value on my vertical axis, that is my energy axis. Now, when the reaction is taking place, you know that the reaction will have to have some energy so that it can start off. Then, once the reaction has started off, there is a point where in the reaction, all the particles, that is particles of R and that of S and that of P, in a certain form, which we call activated complex, are neither a product nor a reactant, but will have to either have to lose a little bit of energy so that it can just go and become the reactants, or can lose more of the energy, and in that case would become the product. So in other words, in the activated energy complex, the substances are at a state of deciding which way to go. Depending on the amount of energy that substance will have to lose so that it can just go into that either product or reactant, depending on the energy the substance is going to lose. Now, if you look at that, if you look at this graph that we have here, you'll see then that there is energy of the particles before the reaction, and that energy is what I call B on my graph. Then once the substance has been given enough energy so that they can react, then I have the higher level of energy now, which is C. Now, then we've got this amount of energy that you require so that the reactants could move to the state where they are ready to go into the reaction. And that energy is called the activation energy. It is called the activation energy. So how would you get that energy? When you're saying energy C, which is the higher energy, minus B, which is the lower energy, and this will give you the activation energy. Now, when you look at my reaction, you'll see then that once the reaction has taken place and my reactants have gone to form my product, you will see then that my product energy is much lower now at A, and in that case, that energy that we see now shows that there is a difference in the energy that substance had before the reaction, which we call activation, which we call energy of the reactants, and the energy that my product, which is the final substance that came out when my reactions have reacted. Now that energy change is what gives us what we call the heat of the reaction, which is mainly denoted by, we may call that delta H, but that's the change in the heat of the reaction. How do we get that? We get that when we're saying the energy of the product minus the energy of the reactants. So in other words, whenever we want to get the heat of the reaction or the change in the heat of these substances, we will say the energy of our product minus the energy of our reactants. And in this case, one would say then that if we say A minus B, since A is of a lower value and B is of a higher value, the value we'll get in this reaction will be a negative value of energy. And hence, it shows us that this reaction lost energy during its course. Therefore, this type of reaction must be an exothermic reaction. So this shows an exothermic reaction. Why do we conclude that way? It is because the energy of the product was higher before the energy of the reactants was higher before the reactants went to the reaction. And when the reaction went on and the product was formed, then the energy of the product became lower. So there was a loss of energy in this reaction. Where else would the energy have been lost to the surrounding? And hence, this reaction is an exothermic reaction. Let's go to my energy curve on my right. If you look at this one again, you would see then that I had my reactants in my hypothetical reaction, which are X and W, that reacted to form a new substance that I called Z. And we would see then that the energy of the reactants, which was in this case A, which is much lower, then in order for the reaction to take place, there was that energy again that was supposed to be supplied, which is also the activation energy. How would you get that activation energy? You will say the energy of the activated complex, in this case, which is shown by that higher value of energy C, minus the energy of my reactants, which is A, that's going to be my activation energy. And you'd realize that when the reaction has gone and the product was formed, the energy of the product now is higher, that is the value of energy at B is higher than the value of energy at A. It means the products have got more energy than the reactants. And such a reaction, it goes without saying that, should have absorbed energy from somewhere. That energy must have come from the surrounding. And then, since the energy of the reactants is lower and I've got more energy in the product, there can only be one reason why there's now more energy. It means that reaction must have absorbed energy from the surrounding. And hence, this type of a reaction is then the endothermic reaction. Why endothermic reaction? It is because it absorbed energy from the surrounding. When we want to calculate the heat of the reaction, here we say the energy of our product minus the energy of our reactants. Now, what is the energy of our product in this case? Our energy of our product would be B, which is of a higher value of energy, minus A, which is of a lower value of energy. And for that matter, it means when we calculate the value of our heat of reaction here, or the change in the heat of the reaction, then we'll get a positive value. So in other words, if the value is positive, it shows us that the reaction is an endothermic reaction. Then, in other words, it becomes easier for us to understand that a positive shows a gain. So therefore, if the heat of direction is delta H is any number that is greater than 0, then it means that reaction is an endothermic. Why? Because a positive value shows a gain. If the change is positive, it means there was a gain in the energy by the product. Then in this case, if the heat of the reaction is less than 0, it means the value is negative. And remember, a negative value shows a loss. It means such a reaction must have lost energy during its course to form the product. Then, quickly enough, we'll have to move over and now do what is very important in chemistry, that we'll just talk much more about chemical reactions we have got to master. Now, we've got what we call collision theory. So if you talk about the collision theory, then what does it say? So the collision theory merely explains the reasons behind why chemical reactions take place in the first place. It is based on some fewer facts or requirements that should be met before the chemical reaction can take place. What are they? So mainly we may just divide them into 3. First, there must be collision of the particles before the reaction can take place. In other words, we are not going to have a chemical reaction unless the particles of a substance collide. And even in that collision, because no two substances will just react to form a new product if particles of one substance and parts of another substance are not colliding so that they can just react and form a new product. Hence, there must be collision before the reaction can take place. And there also must be sufficient energy possessed by the particles so that the chemical reaction can take place. In other words, it means those particles that are colliding should have not more energy than required and not less energy than required so that chemical reaction can take place. What does it mean? It means if the particles have got more energy than required, the chemical reaction won't take place. And also it means when particles have got less energy than what is required for them to react, the chemical reaction also will not take place. And hence we say there must be sufficient amount of energy. Energy that is only good enough for the reaction to take place. Then we also have got the other requirement that these particles must have a correct orientation. So what we mean by that? We mean even if particles now have collided and have got sufficient energy, if their orientation does not allow that the two particles that have collided and have sufficient energy can go into the reaction because they don't have the correct orientation, still there won't be chemical reaction. One can demonstrate this using some few facts. If you can think about, we know that a magnet can pick a coin. If a magnet can pick a coin, if I push my coin and my magnet to such an extent that I've not provided enough energy, the two will never be able to attract each other because one, there might be a larger distance between them, or if that energy is not sufficient to allow them to come and attract, that won't take place. And again, if I throw my magnet with such a lot of energy to an extent that it hits the coin. The probability is it will hit the coin and continue this direction and leave the coin behind. Why? Because that magnet would have attracted the coin, but since I gave it more energy, it will hit and run away from the coin. I'm just giving an analog of what and why would the substances, despite colliding, if there's too much energy, they'll also not be able to react. So that is, and also if one thinks about the orientation, if I may make an example, so when I have these two particles, it's just an example. So if this particle, this side of the particle approaches the other particle, in this case, let me call my particle A and this is my particle B. If it comes in that manner, so there won't be a chemical reaction because the part that needs to fit, the part of B, particle B that needs to fit on A is not coming into play. But if now the orientation is correct, in that case, we would have that part of B coming now in the right manner so that it can fit into A, and in that case the reaction would take place. So therefore orientation that is correct is also essential for the chemical reaction to take place here. Therefore, as we talk about chemical reactions, there are cases where questions ask us, learners, use the collision theory to explain. And when you're arguing about your answers in your race of chemical reaction, you will have to revisit this and understand this clearly so that you can get those marks that are saying use the collision theory to explain your answer. If you have chosen that maybe the reaction rate will be higher, then you must be able to substantiate your answer using what we call the collision theory. Well, so this also is important. Remember, I said there are those three requirements that must be in there so that the chemical reaction can take place. One, we said there must be collision since any two particles cannot react or unless they come together and collide. Number two, those particles need to have got sufficient amount of energy. That is not too much, not too little, just enough so that the reaction can take place. Number three, there must be correct orientation. So when those particles are coming to react, remember they must just bond. So then it means the orientation, the correct part of one particle must be able to nicely fit on the other part of the other particle. Then that is very essential. So those are basic concepts in the collision theory. Then we may just go further and look at what we call, which is also essential, this curve that is called the Maxwell-Boltzmann curve. What do we mean by the Maxwell-Boltzmann curve? This is just only a curve that explains how particles will go into the reaction at any given moment. Now, when we look at this graph, you see that graph on this axis, there is the number of particles, which could be in moles. Then on the horizontal axis, we've got the energy of the particles, or maybe kinetic energy of the particles. When you look at it very closely, you will see then that I may shade this part of the graph. So why do I shade this part of the graph? So not all particles in a chemical reaction just simply go to the reaction. Why is that the case? The collision theory above explained that. Not all particles would have, one, in their collisions, some particles do not even collide, but some particles will collide and do not have the required amount of energy. And some particles will also collide, but they won't be correct orientation. As a result, in every given moment, we would have just that shaded area shows the number of particles that will go into direction. So this area indicates the number of particles that will go into direction. Maybe I should explain why. If you look at that, remember when you come from your left to your right, the energy is increasing. The energy is increasing. Now you see that we've got what we call average kinetic energy. Maybe you would have to know what is average kinetic energy. From the word average, we mean that is the energy that most particles in a substance have. When you look back to our graph, you will see that when I move the particles that have got the most particles, because if you move up our graph along the vertical axis, there will be increase in the number of particles. So when you go to the largest number of particles, it collides with that. So here we've got the largest number of particles, and we've got the energy that those particles have. And hence, this energy is called the average kinetic energy. It is called the average kinetic energy. Why? Because most of the particles here, only at this point, have got this energy, and hence this is energy of most of the particles of our substance, and hence this is called the energy curve. Now, I'll also have to explain to you in the next moment, when we answer the questions of chemical reactions, rate of chemical reactions, I'll have to explain to you why then is it that some reactions will take place faster or at a higher rate, and some reactions will take place at a lower rate. Then we can use the collision theory. The collision theory also addresses the factors that affect the chemical reaction that I'll just be giving in the next video. So then, before we answer the questions in the next video, I would also be touching on this, the application of the application of the collision theory in the explanations of the rate of chemical reactions, and also I'll also be demonstrating how the Maxwell-Boltzmann curve is explained when there is a change in any of the factors that affect the chemical reaction. In that, I'll only exclude the factor that is the nature of reacting substance or nature of reagents, because that one we cannot manipulate amongst these. So for now, until we meet in answering the questions, after we had addressed the factors that affect the chemical reaction, I would say thank you. May you also have your time and watch the next video. Thank you.